Alright, so let's talk a little bit more in detail about what a power flow or load flow study is, and let's define some of the quantities in the power system that we're going to find during a power flow, or again, which is also called a load flow study. And so first, let's talk a little bit more about what a power flow study is and what the importance behind it is. And so a power flow study is very important because they're needed for planning, economic scheduling, and planning of future expansion of a power system, because they essentially tell you how a system operates under steady state conditions and how power flows from generators to loads throughout the system and through transmission lines in the system. And so for a power flow study, the system is assumed to be operating balanced, meaning that the magnitudes between the phases are equal to each other and they're spaced out 120 degrees between each other. So the system is again what's called balanced. And so because of that, we can run our power flow or load flow study in what's called the per phase system, meaning we just draw a single line or a one line diagram that looks like this, and then we use this diagram to perform our power flow study. Because again, we basically just draw one phase and we're assuming that the system is balanced. So if we're talking about A phase in the system, we assume that B phase is lagging by 120 degrees and C phase is leading by 120 degrees for an ABC rotation system. And so in each bus we're going to find four quantities, which are going to be the voltage magnitude V. So this would be voltage magnitude, the power angle delta, the real power P, and the reactive power Q. And so again, for each bus in the system, and for example in the system that I've drawn over here, we have four buses, bus 1, bus 2, 3, and 4. At each bus, at the end of a power flow study, we're going to know the voltage magnitude at that bus, the power angle, the real power, and the reactive power. And so when we talk about power flow studies, we're going to have three types of buses. In other words, every bus in the system is going to fall into one of three categories. And these are what's called the slack bus, S-L-A-C-K, and sometimes that's also called the swing bus. So let me write it over here in parentheses, swing bus. We're also going to have what's called a load bus, or buses, I guess, in plural. And you're going to see here in a second why I didn't call this in the plural, buses. And we're also going to have what's called a regulated bus. So regulated bus, or rather buses in plural again. And so a slack bus is only going to be one bus in the system, and it's going to be our reference bus. And for that bus, we're going to assume that the magnitude of the voltage and the power angle remains constant. And so again, because we're defining that bus as the reference in the system, the voltage magnitude and the power angle stays constant. And so for a slack or swing bus, I'm going to say that we know the voltage magnitude and the power angle. So these are known. And of course, if we know that, then we don't know the real power or the reactive power. So P and Q for slack bus are unknown. And so basically this bus, again, it maintains the voltage magnitude and the power angle constant, and it either supplies or absorbs real power and reactive power such that the power in the system remains balanced. Meaning if we have loads that add up to, let's say, 1,000 megawatts, and we have one generator that supplies 800 megawatts, then we know that that slack bus needs to be supplying the remaining 200 megawatts. So again, the slack bus basically takes up all the difference in the system and either supplies or absorbs that power. Now the second type of bus is the load bus or load buses. And again, the slack bus is just one bus in the system, which is the reference. Now for load buses or regulated buses, that's going to be all the other buses in the system, and it can be multiple buses in the system. So you can have multiple load buses and you can have multiple regulated buses. But basically for a load bus, we know the magnitude of the active and the reactive power that's either absorbed or supplied on that bus. And so we know, again, I'm going to say over here, P and Q are known, but the voltage magnitude and the power angle, delta, are not known. So these are the unknowns for that bus. And so because of this, usually load buses are also called PQ buses. So let me put it over here in parentheses, P-Q buses. For obvious reasons, we know the real power P and the reactive power Q at that bus. So sometimes you'll hear them being called a PQ bus instead of a load bus, but it's the same thing. This is kind of commonly used because, again, for a load bus, you know the P real power and Q the reactive power. Now for a regulated bus, we're going to know the real power P and the magnitude of the voltage V. So these would be known. And of course, then we don't know the reactive power or the power angle. And so similarly as the PQ bus, a regulated bus sometimes is called the PV bus. So P-V buses. Again, for obvious reasons, for those buses, you know the real power P and the voltage magnitude V. Now, regulated buses are usually generator buses, or rather, buses at which generators connect to. And so we know what the real power that the generator is going to be supplying, and we know what the voltage magnitude at the terminals of that generator is, which are usually automatically controlled to keep a constant voltage. And so that's why we know the real power and the voltage magnitude. Now for load buses, as the name implies, those usually are buses in which we only have loads. And if we have a load, we know what the real power and the reactive power consumption of that load is going to be. Now for example, let's say that we wanted to classify the buses on this system over here. This system, or rather this bus number 1, is what I'm going to call my slack bus. So this one right here is the slack. And again, slack is also called a swing bus sometimes. So that's my slack bus. And then obviously buses 2 and 3 over here would be load buses because we have the loads over here. So let's say, for example, that this load was specified to be 100 megawatts. This one right here was 50 megavolt ampere reactive. Let's say that this one was 200 megawatts and that this one over here is 30 megavolt ampere reactive. And so buses 2 and 3 would be, again, load buses. So let me write it over here. This would be load buses. Now for this one, for example, let's say that this is a generator and we know that that generator is set to put out a power, or rather real power, of let's say 100 megawatts. And it's being controlled to maintain its terminal voltage at, let's say, 1.03 per unit voltage. And so this, of course, would be a regulated bus. Regulated bus. And now on our slack bus, we would know the voltage magnitude and the power angle, which again would be fixed for a slack bus. So we can say, for example, that let's say V1 for voltage at bus 1 is equal to, let's say, 1.04 at an angle of 0 degrees per unit. And so what's going to happen in this system when we run the power flow study is that we know that this generator is supplying 100 megawatts and has a voltage magnitude of 1.03 per unit. We know what the loads are here. We would be given the transmission line impedances. So this, for example, could be something like 0.1 plus, let's say, J 5.0 per unit, or something like that. These are transmission lines that connect the buses. And so we would be given the impedances for all the transmission lines in the system. And then once we run the power flow study, we would see how much current flows through this transmission line, through this transmission line, this one, and this one. And I'm just drawing the arrows over here arbitrarily. I don't know what the power flow direction is going to be before I run my power flow study, obviously. But again, when we run the power flow study, we would know how power distributes throughout the system. So if we know that this generator is supplying 100 megawatts and we know what the loads are here, we would know how much power flows through this transmission line, and this transmission line. And again, the difference in power in the system would be supplied by our slack bus. So for example, in here, since I know that this generator is supplying 100 megawatts, but I have a load here of 100 megawatts and 200 megawatts, I would know that my slack bus, for example, is going to have to be supplying at least the difference between those. So at least 200 megawatts plus whatever losses we have in the transmission lines in the system. Alright, so let's talk about the power flow equation and let's derive an expression for the general power flow equation before we dive into the Gauss-Seidel and the Newton-Raphson methods for solving the power flow equation. So if you consider this system over here, and again, I've drawn everything in terms of the admittances, just like we did for the bus admittance matrix examples. And so for example, this generator right here is represented as a current source in parallel with its admittance. And then the transmission lines that connect bus 1 to bus 2, bus 3, and bus n are again represented with their admittances. So Y12, Y13, and Y1n. So notice, of course, here that I've put ... from Y13 to Y1n. So basically we can have any number of buses in between over here. But I'm just going to derive the expression using 3 buses, 2, 3, and n, that connect to bus 1. So I can get an expression for the current I1 as the following. So I1 is going to be equal to, of course, the current that flows through this branch, the current that flows through this branch, and this branch. So if I want to get the current that flows through this branch, I would get that that's equal to Y10 times the voltage at bus 1. So times V1. And then the current that flows through this branch over here would be equal to the admittance, Y12, times the voltage difference between bus 2 and bus 1. So that would be times V1 minus V2. And again, here I'm assuming that the current on this branch flows this way, the current on this branch flows this way, and this way. So they flow out of the bus. So then the current that flows through the branch that connects to bus 3, this one over here, would be Y13 times V1 minus V3, and then plus ... And again, here we could have any number of buses in between. So Y1n times V1 minus Vn. Again, this bus right here is bus n. Now I can rewrite this equation in terms of the voltages at the buses. So I can say, for example, that I1 is going to be equal to Y10 plus Y12 plus Y13 plus Y1n times V1. And so all I did here was I factored out V1 over here. So I have Y10 times V1. Then in here I have Y12 times V1, Y13 times V1, and Y1n times V1. So I just factor out the V1 terms, and then actually I would get minus over here, and now the terms for the bus voltages at the other buses. So Y12 V2 minus Y13 V3 minus ... minus Y1n Vn. And so now let's do one thing. Let's call this bus, instead of calling it bus 1, let me get rid of this. I'm going to call this bus I. And so I can rewrite this equation in terms of the following. So I can say the current I, so capital I, lowercase I, the lowercase being this right here. I can say that that's going to be equal to Vi, so this voltage over here, times the summation from j equals 0 to n of the admittances that connect to that bus. So this term over here. So I can say Y, I, J. and then I need to write down an expression for the remaining terms over here. So I can say minus the summation as j goes from 1 to n, and I can see here that I have y12, y13, y1n. So I would say y, and again I'm substituting I for 1 over here, ij times vj. So j being the other buses. And then of course here j cannot be equal to I. So here I call bus I this bus over here, and then these buses would be 1, 2, 3, 4, 5 through n. And so I will get this general expression for I sub I. Now I know of course that the real and reactive powers at every bus, and let's write down an equation for the real and reactive power at bus I. Let's say that that's going to be equal to P, so real power sub I plus J, reactive power sub I. That's going to be equal to the voltage of that bus, V sub I, times the current I sub I conjugate. Now from here I can say, let's put this equation in terms of I sub I. So I can say I sub I is going to be equal to Pi plus J Qi over Vi conjugate. So now let me call this equation right here on the top equation 1. And let me call this equation right here equation 2. And so now I can combine these two equations, equation 1 over here and equation 2 over here. So I can set them equal to each other, and I would get the following. So I would get Pi plus Qi over Vi conjugate is going to be equal to this whole term over here. So Vi times the summation from j equals 0 to n of Yij minus the summation from j equals 1 to n of Yij times Vj, where j cannot be equal to 1, or rather cannot be equal to I. And so this right here is the general expression for the power flow equation. And from here we can see that this is a system of algebraic nonlinear equations which we have to solve by iteration. And so we can solve them using methods like the Gauss-Seidel and the Newton-Raphson methods, which again are iterative methods for solving a set of nonlinear equations. Alright, so let's talk about how we can use what's called the Gauss-Seidel method for solving a set of nonlinear equations. And so remember that we left off where we derived this equation over here for the power flow equation. And now we know that at every bus we're going to have two unknowns. So for load buses we know the real power and the reactive power. For regulated buses we know the real power and the voltage magnitude. So of course for load buses then we don't know the voltage magnitude or the voltage angle, or rather the power angle. And for regulated buses we don't know the reactive power or the phase angle of the voltage. And so we can use this power flow equation and we can combine that with what's called the Gauss-Seidel method to solve this set of nonlinear equations. And so let's see how we can do that. In the Gauss-Seidel method specifically though, we're going to be solving for the voltage in one way of using this equation, and we can also solve for the real power using this equation as well, and the reactive power using this equation as well. Alright, so what we're going to do here first is we're going to solve for Vi in this equation, and basically we're going to isolate that in one side of the equation. So if I rewrite this equation, I'm going to do one step. First I'm going to bring the terms that don't have Vi on it, so this term over here, to the other side of the equation. So we'll get Pi minus Qi, and again I is the bus I, over Vi conjugate, and then I'm going to move this side, or rather this term over here, to the other side of the equation. So I'm going to get plus the summation as j goes from 1 to n of lowercase Yij Vj. And that's going to be equal to this term over here. So Vi times the summation as j goes from 0 to n of lowercase yij. And now I'm going to isolate vi in this equation, so I'm going to bring this to the other side of the equation. So I'm going to divide all of this by this summation term over here. So then I would get, and let me put vi here on the left. So we get vi, which again is the voltage at bus I, is going to be equal to the following. So pi minus qi over vi conjugate plus the summation as j goes from 1 to n of lowercase yij vj. And all of that over, again, I'm going to bring this right here to the other side of the equation by dividing all of this over that. So over the summation as j goes from 0 to n of yij. So now we're going to introduce a concept which is where the Gauss-Seidel method and the Newton-Raphson method become important. And so basically what we're going to do for these methods is we're going to take an initial guess of what the voltage at every bus is going to be, even though we don't know what the voltage is. And we can do that because we know that in power systems, if everything's operating normally, the voltage at every bus is going to be fairly close to 1 per unit. It's usually in the range of 0.95 to 1.05 per unit. It's hardly ever deviating more than 5% from nominal. And so we can take an initial guess and we can say the voltage at bus X, for example, is going to be 1 per unit with an angle of 0 degrees. And that's what we're going to call our initial guess. And then we're going to use this iterative method to calculate the voltage again based on the quantities that we know in the circuit, so like real power, reactive power at some of the buses, and the admittances. And then we're going to see that we're going to get a different result for that voltage that we assume. So for example, we can assume initially that a voltage at a certain bus is 1 per unit. Then we run through this calculation and we get a value of, let's say, 1.002 per unit. Then we run the calculation again using that 1.002 now as our guess of what the voltage is going to be. And we will get a different result again, let's say 1.0021 per unit. And so we continue the process until we'll get a result that quote-unquote converges to a certain value. Meaning the result that we get from 2 consecutive iterations of this equation are pretty close to each other. So we know that we've reached the real value of the voltage at that bus. And of course we're going to do some examples just to kind of illustrate that. But what I want to introduce now here is the concept of K. So we're going to call K the current, or actually let me say the present, because I don't want to get current confused with amperage. So I'm going to say the present iteration. And so of course then K plus 1 would be the next iteration. So I'm going to say next iteration. And so we're going to define this equation in terms of the present iteration and the subsequent iteration. So for example, I'm going to rewrite this equation and I'm going to put superscripts now that are going to indicate whether the value for Vi, for example, is the present iteration or the next iteration. Because notice here that I have Vi equals, and then I have this whole term over here, but in here I also have Vi. So obviously I can't solve for Vi if on the other side of the equation I also have Vi. But the reason that that's the case is because this is the next iteration and this is the present iteration. So in other words, when we take our initial guess, we're going to plug in that initial guess over here, and then we're going to compute the voltage again, knowing the powers and the admittances and everything else in the circuit. And then we're going to get a new value for that voltage. And then we're going to take that value, put it back in this equation, calculate it again. And that's how our iterative process works. So I'm going to define over here now in terms of the present iteration and the next iteration. So I'm going to say Vi, and I'm going to put it as a superscript in parentheses. So I'm going to say Vi K plus 1. In other words, the next iteration is going to be equal to Pi minus And actually notice here that I missed the J in my equation. So this should be J over here, and J over here. So Pi minus J Qi over Vi conjugate. But this Vi again is the present iteration. So Vi of k, not k plus 1. And all of that plus the summation as j goes from 1 to n of Yij Vj. And this Vj is also the present iteration. And then all of that over the summation as j goes from 0 to n of Yij. So again, here we're going to take an initial guess and we're going to say our voltage at this bus is, let's say, 1 per unit at an angle of 0. Our voltage at another bus is going to be 1 per unit at an angle of 0. We're going to plug that in over here and over here, and then we know the powers, we know the admittances, so we can calculate the next iteration of the voltage at a certain bus. And then we're going to see that that's going to deviate from our guess, obviously, because our guess was just that, a guess of what the voltage would be. But we're going to continue that process until our solution converges, meaning we see that when we run 2 consecutive iterations, we get basically the same result. Now here, when we use this equation, we're always going to use the latest information that we have. So if we compute the voltage at a bus in iteration number 1, let's say, or rather, let's say on iteration number 2, and then we compute the voltage at another bus on the same iteration, let's say iteration number 2, we already know the voltage from the other bus from the same iteration. So we're always going to use the latest value that we get, or rather the latest value that we have for any of the voltages at every bus. So this right here is again the Gauss-Seidel equation for the voltage. And now notice here again that I use the lowercase admittances. And so if you recall from the bus admittance matrix lectures, we know that the terms in the bus admittance matrix are, so uppercase Yij was equal to minus lowercase ij, and then we said that Yii is equal to the summation lowercase Yij. So again, these terms right here on the left side of the equal sign are capital Y's. So those are the terms in the bus admittance matrix. And these terms right here on the right side of the equal sign that have a lowercase y are the actual admittances for a transmission line. And again, this is all stuff that we looked at before in the bus admittance matrix lectures. So now what I want to do is I want to rewrite this equation in terms of the terms in the bus admittance matrix. In other words, the capital Y's over here. So I'm going to say then that I'm going to get the following. So Vi of k plus 1 is going to be equal to Pi minus J Qi over Vi conjugate of the present iteration, so of k, plus, or rather minus, the summation as j goes from 1 to n, uppercase Yij Vj of k. So again, I have here plus, I have here minus, and that's because Yij is equal to minus, or rather uppercase Yij is equal to minus lowercase Yij. So that's all I did there, and then over, all of that over, and then all of that over this right here. So I said summation of Yij, which again we know from the bus admittance matrix that that's the diagonal terms, which is just uppercase Yii. So Yii. So this right here is our Gauss-Seidel equation for calculating the bus voltages. And then here, I should say technically, J cannot be equal to I. So this is the equation that we're going to use for calculating the bus voltages on every iteration of the Gauss-Seidel method. Now we can do the same thing for the power. So we can take this equation and we can isolate the real power and the reactive power. So let's go ahead and do that so we can get an expression for, again, the real power and the reactive power. So if we do that, we would get that Pi, and I'm going to go ahead and put Pi of k plus 1 is going to be equal to, and I'm basically going to move this Vi conjugate to the other side of the equation, and then I'm going to take the real part of that to get the real power. And I'm also going to use these two equations over here to use the terms in the bus admittance matrix. So we'll get the Pi k plus 1 is going to be equal to the real part of this whole term. So Vi conjugate of k times Vik Yii plus the summation as j goes from 1 to n of Yij Vj, and this Vj is of k, and let me close brackets over here, and in here technically again j is not equal to I. And then lastly, for the reactive power over here, we can do the same thing. So I'm going to isolate the reactive power over here by moving this denominator to the other side of the equation and then taking the imaginary part of all that. So I will get that Qi of k plus 1 is going to be equal to minus the imaginary part. And this minus over here came from the fact that we have here P minus JQ. So I move the minus sign to the other side of the equation. So I get minus the imaginary part of this whole term as well. Alright, so these again are the Gauss-Seidel equations. Let me just put all this on a square. So these are the Gauss-Seidel equations for calculating the real power and the reactive power. Again, using an iterative method like the Gauss-Seidel method. Alright, so I think this is a good stopping point for our derivation of the Gauss-Seidel method. In the next lecture, we're going to take a look at some of the assumptions that we need to make when selecting our initial values, as well as how to see when our solution converges. In other words, how we can tell when we actually have a good solution of the power flow equation. Alright, so we derived the equations for the voltage and the real power and the reactive power for the Gauss-Seidel method, which are shown over here. And of course they're in terms of the real power, reactive power, the bus voltages, and the admittances of the transmission lines that connect buses and of generators in the system. And so again, when we have an iterative method like this, what we need to do is we need to take an initial guess as far as what the voltages are going to be. And then from that we can calculate the next iteration of that voltage using things we know, so like the admittances and the power at the load buses. And then we continue running iterations. We're going to see that our solution is going to be different every time we run an iteration. But once we see that the iterations are starting to converge, meaning that the difference between two consecutive iterations is pretty small, then we know that that's the solution to our power flow equation, and we can stop there and use that as our solution. Now there are some rule of thumbs that we need to have in mind when we perform a power flow using the Gauss-Seidel method. So let me go ahead and write them over here. First I'm going to say all buses, I'm going to say the voltage at those buses is going to be somewhere close to 1 per unit. And let's say 0 degrees. And so usually our initial guess for any of the bus voltages in the system is going to be 1 per unit. We know of course that they're not going to be exactly at 1 per unit, but they should be somewhere in the 0.95 to 1.05 range. Because again, for a normal power system, you're not going to have a voltage magnitude of, let's say, 0.7 or 0.6. That's just not feasible. Power systems don't operate in that range. At most, you might see maybe 0.85, maybe 0.8 under very, very extreme conditions. So for example, if there's a blackout about to happen, or a blackout that happened in a neighboring utility or something like that where it's very, very severe, then you might see a voltage that's somewhere in the 0.8 to 0.85 range. But typically that's not the case. And so if we make our assumption that our voltages are operating at 1 per unit, then we can use that as our initial guess here in this equation. That's just a starting point for our iterations. Again, that doesn't need to be correct, that's just an initial guess that we're going to use to plug in this equation and perform the first iteration. Then we're going to get a result for the voltage, we're going to plug that in back into the equation and run a second iteration, and we're going to continue to do that until our solution converges. So all we need to do for this initial guess of the bus voltages is just to get something that's going to be reasonably close to what we expect our solution to be. And so of course, it's always good to pick 1 per unit because we know that the voltage should be in the 0.95 to 1.05 range. And so that's always a good starting point. Now another thing to consider too is that typically load buses have a voltage lower than 1 per unit. So again, it's going to be close to 1 per unit, so usually in the 0.95 to 1.0 range, but it's typically going to be lower than 1 per unit. And so that makes sense because if there's no generation at that bus, then you would expect the voltage to be suppressed a little bit. Again, that's true for load buses. And then likewise, we can say that for regulated buses. Remember that regulated buses are buses that have generators in them, where we're regulating the real power injection and the voltage magnitude. And so the voltage magnitude at those buses is usually greater than 1.00. And of course here I'm talking about the magnitude of the voltage. And so maybe you can make an assumption when you're starting your power flow study that the voltage magnitude at a load bus could be somewhere in the 0.97 range, let's say, and for regulated buses in the 1.02, 1.03 range. Again, the initial guess for the bus voltage is just that, just a guess. And so knowing that you have a load bus and you would expect the voltage to be suppressed a little bit, you can maybe make your guess 0.97, 0.98. And then likewise for a regulated bus where you know that the voltage you would expect it to be somewhere higher than 1 per unit, you could maybe make your guess 1.02 to 1.03 per unit. But I like to just do 1.0 across the board, assume that for all the buses, and then I start my iterations using that guess for all the bus voltages. But this is something that you can keep in mind if you want to take another guess. If you're going to guess something different for a load bus, use something lower than 1 per unit because that's typical, and for a regulated bus use something higher than 1 per unit. Now likewise for load buses, same concept, you would expect the power angle to be lagging. And when I say lagging, of course I mean lagging the slack bus in the system. And for regulated buses, you would expect the power angle to be leading. So we'd expect maybe a load bus to have a voltage angle, or rather power angle, of let's say -5 degrees or -10 degrees, something like that. And for a regulated bus, maybe you would expect the phase angle to be 5 to 10 degrees positive. And so again, you could also take that into consideration when you're taking your initial guess. You might make then the initial guess for the voltage at a load bus maybe 0.98 per unit at an angle of -5 degrees, for example. And for a regulated bus, maybe you could guess 1.03 per unit at an angle of positive 5 degrees. You could do that. Again, what I like to do personally, and this is just a personal preference, I just like to do 1 per unit at 0 degrees for all the buses across the board, and then use that as my starting point. But this is something that you can keep in mind if you want to take another guess. Now in load buses, we know the real power P and the reactive power Q. So I'm going to say these are known. And so we use then this equation to solve for the voltage. So I'm going to say solve for V. Now likewise on a regulated bus, you know the real power and the voltage magnitude V. So these are known. So now you don't know the angle for that voltage and you don't know the reactive power. So what you need to do for a regulated bus is you need to solve for the reactive power Q here, again using an initial guess for VI, and then you can use that calculated value and plug that into this equation and calculate the voltage. So I'm going to say solve Q first, then V. And V again is, you know what the magnitude is, but you need to solve this equation to get the angle. Now when you do that, again, since you know that the voltage magnitude is going to be a certain value, you know that value already, then when you calculate V using this equation, you're going to retain only the imaginary part of that solution, and you're going to calculate the real power using this equation. So again, for a regulated bus, you know P and you know the voltage magnitude V. So you solve for Q first, then use that to calculate V over here. You're going to get a complex value, of course, but you know what the magnitude of that voltage is because, again, that's being fixed. So then once you have that value, you can use this equation. So the real value, or not the real value, the real part of VI K plus 1 is going to be equal to the square root of the voltage magnitude VI squared minus the imaginary part of VI K plus 1 squared. Again, basically what this is saying is you solve for Q first, then you use that in this equation, you get V, but you're going to get a complex number over here, and you know what the magnitude is going to be. So you keep the imaginary part that you get from that result, and you know what this magnitude is, and then from that you calculate the real part of the voltage. That way you have the real part of the voltage and the imaginary part of the voltage for that iteration. And then you would continue to solve this again until your solution converges. So let's talk about convergence for a little bit. Again, now we know that we need to take a guess, put that guess in our equations, perform one iteration, get a solution, then we take that solution, plug it back into the equations, run it again, get another solution, and continue the process until our solution quote-unquote converges. So when I say that the solution converges, let me just write it over here, convergence. What I mean is that two consecutive solutions have a very, very small difference between each other. So for example, I can say that the absolute value of the real part of the voltage at the iteration K plus 1 minus the real part of the voltage at an iteration K, all of that is going to be smaller or less than some value epsilon. So again, this right here is the next iteration, and this right here is the present iteration. So in other words, if you run 5 iterations to get solutions, let's say, this right here would be iteration 5, the value that you get for iteration 5, and this right here would be the value that you get for iteration 4. So you compare the two by subtracting the one from the other, and if that's smaller, or rather the absolute value of that is smaller than some value that you've defined as your accuracy, then you know that your solution converged. And we also have to do the same for the imaginary part. So I'm going to say the real part meets this criteria, and the imaginary part, same thing. And so you compare the two again, you see that there's almost no change in the real part, almost no change in the imaginary part. Then you can say that your solution has converged, and you can take that as the solution for your power flow analysis. And so you might be wondering what's a good value for this, and that depends on how accurate you want your solution to be. Usually I like to do somewhere in the range of 0.0001 to 0.001. And this of course is in per unit. So your solution in per unit should be somewhere accurate to 3 to 4 decimal places. That's considered a good solution, and that's pretty typical for power flow analysis. Of course, you can make this bigger if you don't care about your solution being this accurate, or you can make it smaller if you want your solution to be more accurate. And of course, something that you need to consider is that if you make that too tight, so if you make this, let's say, instead of 0.0001, you make this 0.00000001, then you might need to make several iterations before you get to a solution that's that accurate. So you want to balance the accuracy of this solution and the number of iterations that you're going to need to perform to get to that solution. And so this is usually a good compromise. So it's a very accurate solution, 3 to 4 decimal places, again in per unit. And you should get to that convergence depending on the system and depending on your initial guess how close to the actual solution they are. But you might find that somewhere in the 3 to 7 iterations will give you a solution that meets that criteria. Alright, so I know that this is a lot of math, and so it helps to take a look at some examples to see how we can use this Gauss-Seidel method to perform a power flow analysis. Alright, so let's take a look at an example of how to use the Gauss-Seidel method to develop a power flow solution for a power system. Now that we've defined the Gauss-Seidel method and we've taken a look at the equations for calculating the voltage at every bus and the real and reactive powers through an iteration method. And so for this example, basically, we want to solve for the power flows across this power system over here.